Hello, dear student friends. Welcome to the class of BSc second year mathematics. We are going to study the paper of partial differential equations. Last year we have also studied the paper of differential equation. There we have studied both type of equations, that are ordinary differential equation and partial differential equation. So what is the difference in ordinary and partial differential equations? Here for ordinary differential equations, there is a function of one variable only. In that case, we have considered y is function of f of x, and it involves the total derivative, that is derivative of y with respect to x, or second order derivative of y with respect to x, etc. Here the total derivatives will be involved, and that type of equation containing these total derivatives of different orders is known as ordinary differential equation. But while in partial differential equation, there is a function of several variables, more than one variables. For example, if you consider z is a function of x and y, then we have to take the derivative of z, partial derivative of z with respect to x, and partial derivative of z with respect to y. Their partial derivatives occur, and these derivatives partial derivative of z with respect to x, partial derivative of z with respect to y, or higher order partial derivatives will be there, and such an equation involving partial derivatives is known as partial differential equation. And the meaning of order is same for both ordinary and partial differential equation. The order of the highest differential involved in the equation is known as the order of the differential equation. Highest order partial derivative involved in the equation will be the order of the partial differential equation. So now we shall start the first chapter from this, that is linear partial differential equations of order 1. We are going to study linear PDE of order 1, nonlinear PDE of order 1, and partial differential equation of second order in this paper. First we consider linear partial differential equation of order 1, and at the beginning we shall suppose let x and y be the independent variable. Here there are more than one independent variable. Sometimes it may be say z or u can be considered as function of x, y, z, etc., or t may be also a variable. So this is function of several variables. In that cases, the partial derivatives occur, and the equation involved will be known as partial differential equation. So, but we will consider first as the only two independent variables x and y, and we will assume z is dependent variable. Let x and y be independent variables, and z is a dependent variable. Let the relation between these be z is function of x and y. Z depends on x and y. Now we denote the partial derivatives of z with respect to x and y as follows. So we denote these partial derivatives of z with respect to x by letter p, small p. Different notations we will use, and to simplify or to write this in brief, we denote this by p. Partial derivative of z with respect to y by q. Partial derivative of z with respect to second order partial derivative of z with respect to x as r, and mixed order derivative, second order partial derivative of z with respect to x and y, and that is s, and second order partial derivative of z with respect to y as t. P, Q, R, S, T is the notation, short notation for denoting partial derivatives. So this we shall use this notation. And partial differential equations are very important. They are used in mathematical modeling of many physical phenomena and also in engineering. So partial differential equation express or the heat equation, wave equation are expressed in terms of, or electrodynamics equations are expressed in terms of partial differential equation, because these are function of several variables, and wherever we have to study the function of several variable, partial differential equation occurs there, and therefore these are important. So we have this notation: z is function of xy and the partial derivatives of z are denoted by this. So this is partial derivative, and the symbol, as we know earlier, is curly d. So this symbol has actually no specific name, but sometimes it is called as it is called del or daba or do, but del is used for this operator, and therefore we will say it as a do. So this is a partial derivative of z with respect to x, or we say do z by do x. So we say partial derivative of z with respect to y, or we may say do z by do y, or sometimes it is read as partial d of z with respect to dx, partial d of z with respect to partial d of z by d of y, and so on. So different way the partial derivatives can be read, and now we shall consider formation of partial differential equation. Formation of partial differential equation. In short, hereafter we will write it as PDE, formation of partial differential equation by eliminating arbitrary constants. So actually this is the revision, we have studied this last year also, by eliminating arbitrary constants. And there are two ways of formation of partial differential equation: by eliminating arbitrary constants, and also another is formation of PDE by eliminating arbitrary function. Now here we shall consider let. So suppose the function is phi, let phi of x, y, z, a and b is equal to 0 be a function, or be a given relation where given function or relation where a and b are arbitrary constants. What is meaning of arbitrary constants? Arbitrary constants means constants which can be assigned different values. A is equal to 1, A is equal to 2, A is equal to 3, etc. We can assign the value different values for these constants. Therefore, these are known as arbitrary or any constants. And to form the PDE, we have to eliminate the constants. Arbitrary constants means A and B we have to eliminate. To eliminate A and B, suppose this as equation 1, we shall differentiate 1 partially with respect to x and y. And here we are going to assume as x and y are independent variable and z is dependent variable. So differentiating 1 partially with respect to x and y in succession we get. Now how to take the partial derivative of phi? So we have studied last year a chain rule to find the partial derivative of several variable function. So we have to differentiate this phi with respect to x, and that will be dou phi by dou x. So this is dou phi by dou x plus, and again that is not only the function of x, y is not only the function of x, but it is also function of x, y and z, and also a, b are constants. So partial derivative of phi with respect to x plus, now partial derivative y is to be treated as constant. So therefore its derivative with respect to y will be 0. Y is a constant and its derivative with respect to x will be 0. And but z is dependent on x. See, therefore we have to differentiate z with respect to x using the chain rule, and that will be dou phi by dou z into dou z by dou x. Phi is a function of z. First differentiate phi with respect to z and then differentiate z with respect to x, because z is also a function of x. And thus here we have used the chain rule. And the a and b are constants, so therefore its derivatives will be 0, and this much is the derivative, partial derivative of phi with respect to x. You note this step. And what about the partial derivative of phi with respect to y? As in this case we have differentiated this with respect to x and now with respect to y. So first partial derivative of phi with respect to y, because x is now to be treated as constant, and therefore derivative of x with respect to y will be going to be 0, and therefore only the derivative of phi with respect to y is this one, plus derivative of phi with respect to z into derivative of z, partial derivative of z with respect to y, and that is equal to 0. So these two derivatives we will obtain by differentiating one partially with respect to x and y. Now what should be considered is this notation. See, we have this notation, dou phi by dou z by dou x, or partial derivative of z with respect to x is p. So this is p and this is q. So that is, so we can write this as, that is dou phi by dou x plus, this is p into dou phi by dou z is equal to 0, and this is dou phi by dou y plus q into dou phi by dou z is equal to 0. And we may suppose this as second and third relation, and we can eliminate a and b using equations 1, 2 and 3. So eliminating a and b, eliminate means actually we have to remove these from the relation and obtain the relation which is not involving a and b. Eliminating a and b from 1, 2 and 3. We get a relation of the type we write that as psi, say, and that will be x, y, z, and it will involve p and q instead of a and d. Instead of a and d, now it is in terms of p and q. So is equal to 0, and this is PDE of relation 1. This is the after elimination of a and b. This is the required PDE. Partial differential equation of the relation 1, of the relation or function 1. So this is the procedure. Given the function in terms of x, y, z and arbitrary constants a and b, to eliminate a and b we have to differentiate it. Now illustration for this example we will consider. Eliminate the arbitrary constants a A and B to form a PDE, to form a partial differential equation. Of the relation. Now it may be considered as z is equal to, say, x square plus a into y square plus b. This is the relation that we have. Like this, phi of x, y, z, a, b is 0. This may be shifted on the left side, and z minus this is equal to 0. So how to eliminate the arbitrary constants a and b and obtain the relation of this type, which involves x, y, z and p and q, that we will see. Now we can consider the solution as z is x square plus a into y square plus b. Suppose this relation is 1. Differentiate 1 partially. With respect to x and y. We get. Now that is, first is the partial derivative with respect to x. That is partial derivative of z with respect to x, and the notation is p. We are going to use the notations that we have written earlier. P, that is dou z by dou x, is equal to, when we are differentiating with respect to x, y is to be treated as constant and b is also, ab are also constant, so therefore this is a constant, and the derivative of this is 2x. So this will be 2x into y square plus b. And now the derivative of partial derivative of this with respect to y, that is q is equal to partial derivative of z with respect to y, dou z by dou y. And here now, when we are differentiating partially with respect to y, x is to be treated as constant, so this term becomes constant, and the derivative of this with respect to y is 2y. So this is simply 2y into x square plus a. Simple derivatives are there, and from this we want to eliminate a and b, or actually the given relation involves this term y square plus b. So from this we can write the value of y square plus b. So that is, this gives from the first. Therefore, y square plus b is p divided by 2x. And what about the second relation? This gives x square plus a is q divided by 2y. And thus now we can put these values in 1. So we will get the required partial differential equation. So or we may suppose this as 2 and 3. And now we say using 2 and 3 in 1. So what we have written, eliminate a, b from 1 to 3. From 1, 2 and 3. So here we can use 2 and 3 in 1. So using 2 and 3 in 1. So we get z. Z is x square plus a, that is q upon 2y, and y square plus b, that is p upon 2x. Or this is same as 4 times xy times z, that is 4xyz is equal to p. And this is the relation of this type, xyz pq. It involves xyz and p and q. And therefore this is the PDE of relation 1. So this is PDE of 1. So in this way we can eliminate a and b from relation 1, 2 and 3. and 2 and 3 are obtained by differentiating 1 with partially with respect to x and y. So this is the method that we know earlier also. Now there is another way to form partial differential equation by eliminating arbitrary function that we shall consider. Formation of PDE by eliminating an arbitrary function. Instead of arbitrary constant, here there is arbitrary function. So for this purpose, we shall consider let u and v be functions of x, y, z. Of variable x, y, z and connected by a relation. That is another function. Phi of u comma v is equal to 0, and we suppose this as 1. See, instead of earlier we have considered phi of x, y, z, a and b as 0. Here it is a function. Function of u and v is equal to 0. So this function we have to eliminate. Phi we have to eliminate. But you see, u and v are also functions of x, y, z. Now what we shall do is we differentiate phi partially with respect to x and y. So we write differentiating 1 partially with respect to x and y. We have now here the chain rule is important because this is a composite function. Phi is function of u and v, and u and v are functions of x, y, z, and we want to differentiate it partially with respect to x. So first, phi is function of u and v. So phi is to be differentiated first with respect to u, and then u is to be differentiated with respect to x. So therefore by chain rule this will be dou phi by dou u into bracket the derivative of u with respect to x. But you see, u is function of x, y, z, and therefore derivative of u with respect to x will be dou u by dou x plus, and u is not a function of x only, it is function of y and z also. But when we are differentiating partially with respect to x, y is to be treated as constant. So that means here that derivative dou u by dou y will be 0. And now, but we have differentiate u with respect to z, because z is dependent variable, z is again function of x and y, and plus this will be dou u by dou z into dou z by dou x. So this is one part of the derivative with respect to u. First taking partial derivative of phi with respect to u, and then partial derivative of u with respect to x, plus now partial derivative of phi with respect to v, and again, so I shall write here plus the another part, partial derivative of phi with respect to v into bracket, and derivative of v with respect to x. See, u is a function of phi is function of u and v. Phi is a function of u and v, and u and v are functions of x, y, z. So now when we are differentiating phi with respect to x, then we have to differentiate this via u. First derivative of phi with respect to u, then derivative of u with respect to x. That is we have done here. Dou phi by dou u, and then dou u by dou x. Dou u by dou x will be dou u by dou x plus and y is treated constant, so therefore dou u by dou y will be 0. And but z is dependent, z is also function of x, and therefore we have to differentiate this z with respect to x also. That means partial derivative of u first with respect to z, and then partial derivative of z with respect to x. So that we have written here. Similarly, and second part, now this part with respect to u we have done. Now differentiate pi with respect to v. So this is dou pi by dou v, and in bracket dou v by dou x. Derivative of v with respect to x, and that is dou v by dou x plus dou v by dou z. Dou v by dou z like this. So we are changing u to v. Dou v by dou z into dou z by dou x. So this much is the derivative of phi with respect to x. And now what about the second part? We shall have to consider derivative with respect to y. Both the derivatives we are writing together, and you should note the chain rule of partial differentiation that we have studied last year is important. And now once you understand this, the second derivative, that is derivative with respect to y, can be written easily by replacing x by y. Now partial derivative of this function phi with respect to y. First it is a function of u and v. So first we have to consider it as u, and then it will be dou phi by dou u into partial derivative of u with respect to y, and partial derivative of u with respect to y will be dou u by dou y. X is to be treated now constant, so dou u by dou x will be 0 plus partial derivative of u with respect to z into partial derivative of z with respect to y. So this is, see, in place of x there is y, and plus the second part, again the second part I should write here, plus dou pi by dou v in bracket. Now you see partial derivative of v with respect to y plus partial derivative of v with respect to z, and then partial derivative of z with respect to y. So this is 0. So thus this much is the derivative with respect to x and with respect to y. So you should understand these two, how to write the partial derivatives of a function, composite function with respect to x and y, using the chain rule. Only we have used the chain rule. The chain rule that we have studied in partial derivatives. Now next we will use only the notation. This dou z by dou x, or partial derivative of z with respect to x, is denoted by p, and partial derivative of z with respect to y is denoted by q. So for writing in brief we use that notation. That is, so, or this is the same as dou pi by dou u in bracket dou u by dou x plus, this is p times dou u by dou z plus, and this is dou pi by dou v in bracket dou v by dou x, or partial derivative of v with respect to x, plus this is again p times partial derivative of v with respect to z, and this is equal to 0. We refer this as our second equation, and this one is dou pi by dou u in bracket, this is partial derivative of u with respect to y, plus now this partial derivative is q. We have denoted partial derivative of z with respect to y is q. We write that q into dou u by dou z plus, and the next is partial derivative of phi with respect to v into bracket, this is dou v by dou y plus, and this is q times dou v by dou z. This is equal to 0. This is our third equation. So now what we shall do, we are going to eliminate pi. from these relations 1, 2, 3. When we have used the and differentiating, we get second and free. And here from 2 and 3 we shall eliminate dou phi by dou u and dou v by dou x, because these are there in these both the equations, and we use determinant method to eliminate this. Eliminating these terms, that is dou phi by dou u and dou phi by dou v, these two from 2 and 3. We get. Now we write the determinant of their coefficient is equal to 0. And what is the determinant of the coefficient? Are these brackets. So dou u by dou x plus p times dou u by dou z, and second is dou v by dou x, partial derivative of v with respect to x, plus p times partial derivative of v with respect to z, and second row of the determinant is partial derivative of u with respect to y plus q times partial derivative of u with respect to z, plus our next element is partial derivative of v with respect to y plus q times partial derivative of v with respect to z. So u and v should look distinct, and this must be equal to 0. So this is the elimination of these two terms from the two equations, because they will have unique solution, and therefore the determinant is 0. Now we will expand this determinant. So while expanding the determinant, we write the coefficient of p and q. So I shall consider the expansion of the determinant by taking p common. If you take p common, the multiplication of these two will be there in bracket. So dou u by dou z. So this is arithmetic part, you may verify. Dou v by dou y, product of these two, minus the product of these two, minus dou u by dou y into dou v by dou z times p, plus. Now what about, there is negative sign of this, so we are collecting the coefficient after expanding, and q, see, this is dou u by dou x, product of these two, into dou v by dou x, dou v by dou z, minus q, the coefficient of q, dou u by dou z into dou v by dou x times q, and is next what are the remaining terms. Remaining terms, so we will write dou u by dou x into this, dou u by dou x into dou v by dou y, product of these two minus product of this, minus dou u by dou y into dou v by dou x is equal to 0. This is 0. One thing is to be noted, that what about the term of pq? See this product, p into q, dou u by dou z into dou v by dou z, and here also p into q, dou u by dou z into dou v by dou z, that cancels in subtraction, in expansion of the determinant, and therefore we get this term. Now what we do is we multiply throughout by a negative sign and shift this last term on the right side. So the equation becomes so if you multiply by negative sign, this will be positive and this is negative, so that will be dou u by dou y into dou v by dou z minus, you can verify this, p, plus next is, this is positive and then this is negative, we are changing the sign, So it is dou u by dou z into dou v by dou x minus partial derivative of u with respect to x into partial derivative of v with respect to z times q. And this will be positive, this will be negative, but we shift the term on the right side and therefore they will have the same sign, is this one. Now this can be written in form of another determinant. So that is, now we will write this in terms of, say, dou u by dou y, dou u by dou z. Dou v by dou y, dou v by dou z. Into p plus, this is to be written as dou u by dou y, or we can consider this as the dou u by dou z into dou u by dou x, and dou v by dou z into dou v by dou x times q. Check it whether these values are the same, and right side is the determinant see dou u by dou y into dou v by dou z minus dou u by dou z into dou v by dou y. See, this must be dou u by the coefficient of v, dou u by dou y into dou v by dou z. So this must be corrected. It is y. Dou u by dou y. See, product of these two minus product of these two. Dou u by dou y, or here we have this is the first term, and p. P dou u by dou y, and then dou v by dou z. So this must be u v and y and z. So dou u by dou y, dou v by dou z minus dou v by dou z into so this is u v and y z. This u v y z, but it is it must be dou v by dou y, dou v by dou y, and dou v by dou y and dou v by dou z. So this must be v. This must be v. So we will have to check this. This is p dou v by dou z, and this is dou u by dou y. The coefficient of p we are collecting. So, okay. And what about this dou u by dou z, dou v by dou x minus dou u by dou x, dou v by dou z. So this is right. And this is dou u by dou x into dou v by dou y minus the product of these two. So that is also correct. So what needs to be corrected is this must be dou v by dou y. U and v, y, z, v, y, z. So this is actually dou u by dou z, dou u by dou z, and so dou u by dou y, dou v by dou z, and dou u by dou z into dou v by dou y. So we have changed the sign. So sign is changed and we got this term. Yes. and what happens here is this must be uv and yz. So this term is the same, dou u by dou z. So dou u by dou z, dou u by dou z into dou v by dou y. Now you see dou u by dou z into dou v by dou y. It is the same. Dou u by dou z into dou v by dou y. Dou u by dou z into dou v by dou y. Now it is right. So we have verified these terms. And now what these determinants are known as Jacobians. So this is Jacobian. First determinant is Jacobian of u and v with respect to y and z. So that is, and that Jacobian is denoted by this notation, Jacobian of u and v with respect to y and z into p, and it has exactly the same determinant value. So how dou u by dou y first term, then dou u by dou z second term in the first row, and then second row dou v by dou y, dou v by dou z, and plus the next is Jacobian of again uv, but now with respect to z and x. Now you can verify likewise. Dou u by dou z, dou u by dou x. First take the partial derivative of u with respect to x, z and x, that forms first row, and then take the partial derivative of v with respect to z and x, that forms the second row, and is equal to, the right side is also a Jacobian of u and v with respect to x and y. So these are known to be Jacobian. You have to, for time being we have not studied and you assume it. So these differentiate these determinants represent these Jacobians. And again this is, that is capital P into small p plus this is, we denote capital Q into small q, and is equal to R. So thus here the function phi is not there. Phi we have eliminated, and this is the partial differential equation of relation 1 by eliminating arbitrary constant. So this is the required PDE. Required PDE of 1 by eliminating arbitrary function phi. So this equation is important. It is also known as Lagrange's linear PDE, and we are going to study this equation furthermore next time. So please verify the steps and try to understand. Thank you.